We're going to cover today what I was going to cover on Friday, but the technical difficulties got in the way. So we are going to start with assembly programming with some general principles of assembly programming. First and foremost, assembly language, assembly instructions do one thing only. It's very important to remember. They only do one very simple thing. They are the very basic level of instructions that a computer can understand. In this language, most of the instructions are 16-bit instructions, although some are 32-bit. What that means is instructions are converted to binary numbers. Just a string of ones and zeros. That is what the processor actually runs. So, if you have only 16 bits of data in the instruction, that means you can only do, 65,536 different things. And that may seem like a lot, but when you look at the arguments for the instructions, those 65,000 plus possibilities dwindles down very quickly. Now, the structure of a assembly instruction you have the mnemonic. Then you have potentially argument 1, comma, argument 2. No semicolon after the instruction, no period or anything like that, just the mnemonic, the instruction itself. The mnemonic is going to be 2 to 4 letters long. The arguments are going to be registers or numbers. And I put the angle brackets there because not all instructions have arguments. Those are optional. If the instruction doesn't have a argument, it just is the mnemonic and then the next line. And actually, let me clarify this. It is the comma is optional if there is a second argument. No instructions have 3 arguments. It is just going to be 1 or 2, 0, 1, or 2 arguments. So we'll give a real quick sample of what a, well, argument 1 is the destination register, destination of the action. And arg2 is the source. So a move operation, where you're moving data from one place to another, the source will be the second argument, the destination will be the first argument. If you're going to add 2 numbers together, the argument 2 is going to be added to the first argument, and the answer, the result, will be placed in the destination argument. So keep in mind that format. The destination is going to be the first argument. The source, where the data is coming from, is going to be in the second argument. And I'm going to go ahead and pull up the instruction set. And pull out a regulation instruction set manual. The instruction set manual, like the add, you can see here it adds 2 registers together without the C flag and places the result in the destination register, RD. So the format of the syntax of the statement is add, RD, the register of the destination, and RR for the other value. This operates on any of the 32 32 registers, and the program counter increments by 1 after the operation takes place. So That is the this is the standard format for a instruction in the instruction set manual. It also tells you what the status register does. It for those of you that don't that haven't taken discrete structures yet, these symbols here are the arrow pointing up means and, a logical and the V indicates a logical or. This symbol here, if you remember from digital logic, is exclusive or. And the bar over the bit is going to be invert. So in this case, the result, bit 7, bit 6, bit 5, bit 4, 3, 2, 1, and 0, if they're all inverted, R7 is inverted and R6 is inverted, and all this are 0. Basically, if all the bits are 0, it will be a 1 in the 0 flag of the status register. That gives the Boolean formulas for the various status register flags, as well as a verbal, a textual explanation of the result. What to expect. Oops. Now, like I said earlier, the instructions are 16-bit. This one is a 16-bit instruction. So if you want to translate by hand the instruction, the add operation, into binary, it would be 4 zeros, 1 1, and then the bits representing the number from 0 to 31 in R for the source register, and then the bits of the destination register. So you can see that the argument values are embedded into the 16-bit opcode, operation code. So with this instruction set manual, you could write a program, if you so desired, to translate assembly code into binary that could be run on this processor. All the information that you need to do that is included in this instruction set manual. Now, I skipped over a whole area, a whole section. When you get to the programming part, when you first start the power on the processor, the program counter, the PC, equals 0. So the instruction at the lowest point in the memory, the flash memory, is going to be the one that's going to be executed. So the program counter equals 0, and then it would increment or be adjusted accordingly, depending on the instruction that is at location 0. Now, typically, at least how I do it, and how a lot of people do it, the first instruction typically jumps to the startup routine. It is also called the reset. The reason why it jumps from the first instruction to a startup routine is because the first several dozen lines, memory locations of the flash memory are reserved for the interrupt vector table. That's the word I was looking for. The interrupt vector table. What that is what an interrupt vector table is a sequence of let's see here, ADC ready. I'm just putting examples out there. What the interrupt vector table is a series of jump statements which jump to the appropriate interrupt handling routine. These are labels. Located elsewhere in the in the program. For the jump instruction, you can look in the instruction set manual under JMP. It can jump anywhere in the program memory space. So you would have this interrupt vector table, and then at some point you would have reset, colon, and then whatever instructions you want it to run when it first starts up. Now, what the jump routine does is, what the jump instruction does is loads the number represented by the label, which is the location of the location in the program memory of the location that you want to jump to, and it loads that. Say this is at 0x015AC. Okay. What it does is it loads this number into the program counter. So the program counter starts looking at this location. Very basic stuff. It's not looking for a string reset. It just, the assembler, the compiler translates the label into a number that it can, that corresponds to the memory location of the instruction that it's in front of. So, let me see if I have a sample. File viewer, scratch. I do not. I did not put it on this flash drive. Or did I? Template. Aha. There we go. Oh, okay. It came out weird. But the JMP. This is at the beginning of the memory space. JMP start the label, and you would have a series of jump commands corresponding to the various interrupts, and then you would jump over all that, all this. This is a template that I'll put up on, if I haven't already, I'll put up on Canvas so you can start with this so you don't have to type all this stuff in. But here's the label for the where that jump corresponds to. Rather than having a number there that represents the location in memory, we could just use labels to indicate that, and the assembler will figure out which number is supposed to go there. But this is another instruction that we'll be dealing with a lot, the LDI instruction. R26, register 26. And a number. That's the number that is being loaded into register 26. And that keeps popping up. So that follows the same structure as I showed earlier. It has a load operation where the destination register is given first, and the number that you're loading into that register is given second. Semicolons, you might figure out from looking at this, represents a comment. So if you want to comment your code because it's not obvious what's going on, semicolon first, type out your comment. It's ignored by the compiler. But we'll get into these instructions a little bit more as we go along. But and you can see, oops, clear. You can see that some numbers are represented in hexadecimal. Some numbers are represented in binary. Hexadecimal, binary. Rarely do you use the decimal versions of numbers in an assembly program. So keep in mind 0x for hexadecimal, 0b for binary. Are you sufficiently confused? I was just trying to give a basic overview of assembly programming, and it occurs to me that I forgot to, there was a whole section that I forgot to cover before this, having to do with the memories of the processor and what exactly are peripherals. I will get into that on Wednesday, kind of step back and do that. And then we'll get into how to program peripherals, because a computer has to, a peripheral is a part of a computer that deals with the outside world, typically. And a computer that can't interact with the outside world is basically pointless. You have to be able to interact with data coming in, whether it's a keyboard or mouse or whatever, screen. In the case of the for this semester, we'll be dealing with knobs for input and LEDs for output. So how do you deal with those with the outside world as far as that's concerned? But we will get into that more on Wednesday. In the meantime, try not to be overwhelmed by the oddness of the assembly language or the instruction set manual. But if you get a chance, I will put up the template program, the template file on Canvas. You can look at that in a text editor. You can clean up the where the come on. You can clean up the comments and stuff like that as you please, as you might wish to. But I will get that on. Get this file on Canvas so you can look at it and get a little bit familiar with what you're going to be seeing over the next few weeks, or well, between now and the end of the semester, really. But in the meantime, have a good day. See you on Wednesday.